Chapter 2 of this book is the physics behind conductors and semiconductors. Instead, we will concentrate on Chapter 3, which has practical applications, and there are no homework assignments for Chapter 2. The most important concept from Chapter 2 is that there are two types of material, N-type, which accepts electrons, and P-type, which accepts holes, and that when the two materials are brought together, there forms a depletion layer, and this depletion layer requires zero point 0.7 volts to overcome. That is, in order for the device to conduct, you must have zero point 0.7 volts. For practical purposes, we now have a device called a diode, and it has an anode and a cathode, positive and negative as you see in the drawing. We always need to find the current through the diode. In the drawing shown above, we see that the diode is forward biased. We agree that the diode drops zero point 0.7 volts. That means that in order to calculate the current, we can say that we have 9.3 volts left over for the resistor, and therefore the current through the diode and through the resistor is 9.3 volts divided by 1 kilo ohm, 9.3 milliamps as shown in the drawing. Because the diode drops only zero point 0.7 volts, we say that it is functioning very much like a mechanical switch, because a mechanical switch, if it were closed, it would conduct current but would drop very little voltage, just like the diode. In the case of a diode in reverse, we don't do any calculations. We assume that the current through the diode is zero because the diode is reversed. Because we have zero current, that means we have an open circuit. And when you have an open circuit, the voltage across the diode will be the source voltage, in this case 10 volts. Please ignore the mistake. Voltage across the diode is 10 volts. Once again, the circuit functions like a mechanical switch, because if a mechanical switch is open, we would have zero current, but if we measure the voltage drop across the switch, we would see the source voltage, in this case 10 volts. In order to calculate the current through the diode in more complex circuits like shown above, we need to use Thevenin's method. First, remove the diode and label the empty terminals A and B and pretend that you put a voltmeter from terminal A to B. The 1 kilo ohm resistor is effectively out of the circuit, so the Thevenin voltage is the voltage drop across the 3 kilo ohm resistor. We calculate the Thevenin voltage with the formula shown above, and we find that it is 12 volts. Because the 1 kilo ohm resistor is out of the circuit, then the Thevenin resistance is 6 kilo ohms in parallel with 3 kilo ohms. And when we do the calculations, we find that Thevenin resistance is 2 kilo ohms. We have now calculated Thevenin voltage and Thevenin resistance, but now we have to take into consideration the 1 kilo ohm resistor. Including the 1 kilo ohm resistor, now we have a total resistance of 3 kilo ohms. If we put the diode back in place, now we can calculate the current through the resistor, which is also the current through the diode. We can say that the current through the resistor is 12 volts minus 0.7 volts due to the diode drop, and then divided by 3 kilo ohms, which gives us a total current of 3.77 milliamps. And then we say that the current through the resistor is also the current through the diode.